So, but I don't see you now. How can I see you? View, standard, okay. So the classical rigidity theorem, or the most classical, the three most classical rigidity theorems, so which are basically local rigidity, strong rigidity, which is most of rigidity, and super rigidity. So that's the three classical. This is usually called most of rigidity. This is Margulis super rigidity, and local is after usually attributed to Whale, but there are other people involved. Also in the super rigidity and most rigidity, there are other people involved. Maybe I will mention some of the history. Basically, I will describe the theorems, so we understand the statements, and how to use them. So I'll deduce some application from each theorem. I will not give a proof for the theorem. The proofs are a bit heavy, so it's like each require several lectures. I will not do it in this course. So we'll start with the local rigidity, but before that, let me recall you the notion of, I don't remember exactly what we did already. So if I say something that we did, so remind me. So did I define what is an irreducible lattice? Okay, so definition. Let G be a semi-simple Lie group. A lattice gamma in G is called reducible if there is a non-trivial decomposition G equals G1 times G2 such that gamma intersection with G1 cos gamma intersection with G2 is the lattice. If it is a lattice, then it is a finite index inside gamma. So gamma is commensurable to a product. That's what you say. And otherwise, gamma is called irreducible. And
so you assume G is center free or simply connected, right?
I assume that G, no, I don't need to assume that here. Why?
I mean, it's not, it doesn't need to be an actual product, right?
Okay, if you want, you say that there might be some finite intersection. Yeah, if you assume that, it's center free, then it's a product, and otherwise you are right. Yeah, if you assume that it's adjoint or simply connected, yeah, in general there can be. We allow usually semi-simple group with centers, and then you write that there might be intersections. So to be more precise, you should write like this. Yeah, there might be intersection. But if G is adjoint, like center free, then it's an actual product. And rigidity theorem applies in that generality of irreducible lattices, that's why I wanted to say this definition, a remark that a consequence of the Borel density theorem is that if gamma in G is irreducible, then the projection of gamma to any proper factor is dense, and the intersection of gamma with every proper factor is central. Then say for any G1 in G normal, we have G1 intersection with gamma is central, which is trivial if we assume that G is center free, and the projection mod G1, gamma times G1 is dense. So, and this is actually equivalent to being irreducible. So a lattice is irreducible if and only if the intersection with every proper factor is trivial or central. And if and only if the projection is dense. When people discuss more general groups like locally compact groups, these various definitions do not coincide, and usually what is common to assume, which is easy to use in application, is this definition. So in the general context, when you consider product of a locally compact group, you usually assume that want to say that a lattice is irreducible if the projection to every proper factor is dense or at least non-discrete. So yeah. Okay, so let's start with local rigidity. So let G be a semi-simple Lie group.
Tsachik, why is it central again? G1 intersecting gamma?
This is I said it's a proposition or a theorem. I said it's a consequence of the Borel density theorem. I didn't explain why. If you want, you can say that the intersection of gamma with the G1.
It's not every normal subgroup. It's every factor.
For every normal subgroup. For every normal subgroup of G, yes, the intersection is central. Yeah. It's correct as I said. So it's a consequence of it's not trivial. I mean, you have to prove. It's not very hard, but since we didn't prove Borel density, I will not explain this now. I just wanted to explain a bit the definition. I think maybe we'll dedicate one lecture to Borel density and its application. So this is one of the application of, but this is described very well in Raghunathan's book. So Raghunathan's book is not a good reference for Borel density theorem because the proof he gives is the original proof, which is way too complicated compared to more recent proof. But it's the discussion about application is very nice. It's very well. So if you want to read the application of Borel density, Raghunathan's book is a good reference. But maybe I'll dedicate a lecture for that. And in particular, yeah, I think I should do it, but in the more general context of invariant random sub. For now, I just want to say a bit about irreducibility. I will not spend time on that. If you want example, the canonical example, you take gamma to be SL2 z square root of 2, and this is embedded in SL2R cross SL2R, where in the first factor it's just the canonical embedding, and in the second it's the Galois conjugate when you send square root of 2 to minus square root of 2. Then the image is discrete and of cofinite volume and not co-compact, so it's a lattice in the product. And then it's easy to see that the intersection with each factor is trivial and the projection to each factor is dense. So so that's how you should think of an irreducible lattice. So let G be a semi-simple Lie group. Let now gamma be a finitely generated set, a group. Then we denote there is the variety of representation of gamma in G. Is given by, is written home gamma G, which is the set of all maps from gamma to G, all homomorphism. Now, if G has some additional structure, then home gamma G inherits this structure. So home gamma G inherits many structures, many or some, I don't know, some structures from G. For instance, okay, so what do I mean by that? So of course, if G is finite, then home gamma G is a finite set. That's one. If G is a discrete group, in our case, G is a semi-simple Lie group. So G is in particular is a topological group. So home gamma G is also a topological space. So so what is the topology? You can think the topology. Okay. The topology is the pointwise topology. The pointwise to convergence topology. What does it mean? That Fn converge to F if Fn gamma converge to F of gamma for every gamma in gamma. But it's enough to check this for the generator. So you can think of a home gamma G, you can think of it as a subset of sigma to the G. If sigma is a generating set, so yeah. And when you think of it in that way, you can also easily see that if G is algebraic, a finite algebraic group, so you know that every, let's say, adjoint semi-simple Lie group is a Q algebraic group, is algebraic group defined over Q. So also this will be an it's
Tsachik?
Yes.
You mean to add G to the sigma, not sigma to the G.
Thank you. G to the sigma. Thank you. You can actually think of it. You can think of if gamma is given by a set of relation, you have a presentation with generator and relation, maybe infinitely many, but maybe in our case it will always gamma is finitely presented. So home gamma G is the subsets of all, if you want, all, you can view it as all, let's say, tuples inside G to the sigma, such that R of G equals the identity for every relation. So in that way, you can also think of it as an algebraic variety. So if G is a Q algebraic group, then gamma is then home gamma G is a fine algebraic variety defined over Q also. So okay, that's enough for us. So in particular, when G is a semi-simple Lie group and Q algebra and let's say a real algebraic group, or defined over Q, I mean, it's an algebraic group, a group of matrices with polynomial that determines it as a variety are defined over Q, but I consider the real point of it. So these are all the groups we are interested in. That's every adjoint semi-simple Lie group as such a structure. Then also home gamma G, if gamma is finitely generated group, is also a topological space. And an algebraic variety, a real algebraic variety defined over Q. Yes, sometimes you care about other structure, like if G is a measurable group, if G admits a Haar measure, then also this will be a measurable space, and you inherit the measure. If G is a compact group, then this will be a compact space, and so on. But in our case, we care about these two structures. Okay, now definition. F in home gamma G is locally rigid if there is a neighborhood omega containing F in this topological space, such that every phi in omega, there is G in G, such that phi is F to the G. So that means that phi of gamma equals G F of gamma, G inverse for every gamma in gamma. So then this homomorphism is called local origin. And a subgroup, gamma in G, is locally rigid if the inclusion gamma into G is locally rigid. meaning that, yeah, and I don't know if I want to add this. Rigid. So maybe I want to require a bit more. If there is G in G, let's say close to 1, close to the identity. So the smaller this neighborhood, I want this conjugating element to be, okay, phi is a small deformation of F. This is also a deformation of F, and you want. I think you don't need to require it. You can prove that if such a G exists, then you can take such G near the identity. But I don't care to require it. Okay, this is a local rigidity. Now the classical theorem about local rigidity so what's how should I state it? So first, it was first stated for compact group, for co-compact group. Okay, so this is by Weil, Calabi, and Selberg. I think the order is opposite. So Selberg proved it for SLN, Calabi, I think, proved it for hyperbolic manifold or complex hyperbolic manifold, and Selberg, the general case, proved the following. Let G be a semi-simple Lie group, not locally isometric to SL2R. So in particular, not if I only consider a adjoint group, so the assumption is that G is not PSL2R. Then every uniform lattice is locally rigid. That's the theorem. So in SL2R, we know that this is not true. If you are familiar with Teichmüller theory, we know that lattices admits no lattice in SL2R is locally rigid. Every lattice admits a positive dimension variety of deformation, which is called the moduli space or the Teichmüller space associated to the surface. So no lattice in SL2R. So this is like a distinction between SL2R and other semi-simple groups. So that's, and by the way, jointly with Ariel Levitt, we extended this theorem to any group of isometries of cut-zero spaces. So, so we show that under certain condition, if you have any group of isometry of cut-zero spaces and the space is not the hyperbolic plane, then every uniform lattice is locally rigid. I should assume every irreducible. If it's enough actually to assume that it's irreducible in the SL2 factors. If G doesn't have factors locally isometric to SL2, then you don't need to assume that. And if it has, then you just need to assume that the projection to each such factor is dense. Then every lattice is locally rigid. So that was the first result from the 60s. So Weil theorem is from 1962. Selberg proved it for SLN in 1960. Actually, this could be a wonderful thesis for a student to take for a master student to take, but also it could be like a nice paper for a PhD student to take Selberg's proof and do it in the generality of all semi-simple group, because Selberg consider only SLN, but the proof can be, I think, I don't see why not, can be generalized to the general case, and it's a very clever proof. So I think it's it should be done at some point. Later, Margulis and who else? Maybe I should say Prasad, Raghunathan. Okay, this was generalized. I should say by Margulis to higher rank, and Prasad Raghunathan, I think. But anyhow, it follows also from correlate super-rigidity theorem that I will mention later in the rank 1 case. No, it doesn't. So, okay. So by Margulis and by Prasad Raghunathan to non-uniform lattices. And now the theorem is the following. So let's say, and the theorem is that now we need to assume that G is not locally isometric to SL2R or SL2C. If G is not locally isometric to SL2R or SL2C, then every irreducible lattice is locally rigid. So, okay, so I had to add this assumption because non-uniform lattices in SL2C are not locally rigid. And that's another special case. And the fact that they are not locally rigid is very interesting on its own, and it's allow you to construct very interesting examples of hyperbolic manifolds, tree manifolds, by closing a cusp, a procedure which is called hyperbolic dense surgery. But I should remark that also there is some weaker there is a weaker version which applies to non-uniform lattices in SL2C. So remark non-uniform so uniform lattices in SL2C are locally rigid, but non-uniform lattices in SL2C are relatively locally rigid. in the variety of representation that preserve a unipotency, so that send unipotence to unipotent. So what do I mean by that? For instance, if you consider gamma to be SL2, let's say Z of I, which is a lattice in SL2 C. So inside gamma, if you consider the following matrix is a unipotent matrix, and if we consider so I want to consider only representation of gamma that send such matrices to unipotent. So every unipotent, so I consider let's say I need a name for that, home, let's say U gamma SL2C will be all the map F from gamma, all the homomorphism to SL2C. Homomorphism such that for every gamma in gamma unipotent, F of gamma is unipotent. Then this is a smaller variety. It's also defined over Q. It's also has nice properties. And inside this variety, this gamma is locally rigid. So, so such a lattice is locally rigid inside this variety. So the fact that such lattices are not locally rigid allows you to construct very interesting example of hyperbolic manifolds or of lattices in SL2C, which have interesting properties. And the fact that it is locally rigid within a smaller subvariety allow you to prove some theorems about such lattices. So so now I describe the theorem. So the classical theorem speaks about uniform lattices. The classical theorem speak about uniform lattices. This one, it's called Weil local rigidity usually, due to Weil, Calabi, and Selber, and Margulis proved super rigidity, which I'll mention later today, which is in particular imply local rigidity for higher rank lattices, independently if they're uniform or non-uniform. And Prasad and Raghunathan studied the structure. They have a paper about the structure of rank 1 lattices, and in particular, they proved several results there, but in particular, they proved local rigidity, except in the case where G is SL2C, which the theorem is not true, but a weaker version is true. So if you consider, if you have a three-dimensional manifold, so it's something that, let's say, okay, this is how we visualize surface with a cusp, but suppose it's three-dimensional. So the fact that it's not locally rigid allows you to cut the cusp and glue some solid torus here in a twisted way, and get a compact manifold, which in a sense approximate the non-compact one, and you can do it in various ways. you can do it farther along the cusp and get a sequence of compact manifold converging to a non-compact one, and this allows you to find interesting example of hyperbolic manifold. But if you don't allow, when you translate it to groups, what you do, you take a deformation of this group, of this lattice, and some unipotent element become elliptic. They become element of, they become elliptic elements. So the eigenvalue 1 preserved its absolute value, but does not preserve the fact it's 1. And this allows you to do that. But if you don't allow that and you insist that the eigenvalue 1 stays 1, then you don't have such deformation. And that's in that sense, such lattices are also locally rigid. Okay, in SL2R, you cannot even hope for that. In SL2R, non-uniform lattices are virtually free group. So if you have a free group, you can deform it in any way you want. And you cannot expect for even a weak version of local rigidity. So in SL2R, you don't have that. So that's why the assumption here is that, yeah. Okay, applications. So I want to deduce 2 applications, which I like. My favorite application of local rigidity are first, it has some algebraic nature, the first one, and this is what Selberg realized, and I think that was his motivation to formulate the arithmeticity conjecture, the famous arithmeticity conjecture. So here is the result. The result is the following. So corollary. Let G be, let's say, okay, let's formulate it precisely. So let G be a Q algebraic group. And G is the corresponding Lie groups of real rational, the group of real point. G, the Lie group of a real point. So every semi-simple Lie group, every adjoint semi-simple Lie group can be viewed in such a way. Let gamma be finitely generated locally rigid subgroup. Then there is G in G, then there is a number field so a finite extension of Q, K, a real number field, so it's subfield of R, but it's a finite extension of Q, and G in G such that gamma conjugated by G is contained in the group of K point. In particular, the eigenvalue, every eigenvalue of add gamma for every gamma in gamma is algebraic. And this, okay, this is a very general result. So here is, for instance, example of a corollary. The matrix pi 1 over pi is not contained in any lattice in SL2C because pi is not algebraic. And so you see, this is not about arithmetic. Soon I will remind the definition of arithmetic lattice. This is much more general. So if you want, in some sense, if you attended Paul talk, so you know that eigenvalues are related to the Mahler measure, which related to the displacement length, which related to the length of closed geodesic in locally symmetric manifold. So if you want, in the right normalization, if you have of the Riemannian metric, if you have every three-dimensional hyperbolic manifold, if you measure every closed geodesic, the length of that geodesic is algebraic. And you don't need the manifold to be arithmetic. It's true for any three-dimensional manifold, for any hyperbolic manifold of any dimension, and for every locally symmetric manifold, actually, except it's not true for hyperbolic surfaces. In hyperbolic surfaces, again, you have the Teichmüller theory that allow you to construct surfaces with the geodesics of arbitrary length. Every real number can be the length of a closed geodesic in a two-dimensional hyperbolic surface. But in three-dimension already, you are restricted to algebraic length.
Tsachik, didn't we exclude SL2C beforehand?
Yes, we excluded SL2C, but then I said that in SL2C you don't have
relatively local.
You have relative local rigidity, and this is enough for the application.
So in the application, you can write relative local rigidity instead of...
Yes, yeah. I will explain how to prove the application, the corollary. I will explain the proof of that corollary, and you will see that you can apply it for also with the relative local rigidity. So
when you use the corollary, the G is not SL2.
Sorry?
The Q algebraic group you are using in order to use the corollary, not SL2.
Restriction of scars.
Yeah, here in that corollary, G could be anything, not even it doesn't even need to be even semi-simple, but I assume that gamma is locally rigid, and it's enough to say relatively. But I didn't want to say, because I just give you one example of relatively local rigidity, which is local rigidity of non-uniform lattices in SL2R, and then the definition of the variety was that unipotent tend to unipotent. And yeah, if that's all we allow, then it's fine. I mean, you can, yeah. Is it clear, or? Let me just explain how.
I think what Tal meant to say that the special G, the algebraic G here, is not SL2 in the corollary.
Yeah, it cannot be SL2 because
I think the restriction of scalars of SL2.
So it could be SL2, this, because gamma is not necessarily a lattice. Gamma here is locally rigid subgroup. So if you give me SL2 and a subgroup, and for some reason you know that the subgroup is locally rigid, then you can still deduce this. Lattices in SL2 are not locally rigid, but there are other groups in SL2 which are locally rigid. For instance, there are some dense group like SL2 Z square root of 2 is locally rigid. So it's a finitely generated group which is locally rigid. So this corollary applies to anything which is locally rigid, and you apply it usually in conjugation, like together with a local rigidity theorem, because then local rigidity theorem tell you to give me a lattice, I know it's locally rigid, and now we say, okay, if it's locally rigid, I can conjugate it into such a group, the group of real points. So the corollary for lattices is that if gamma is an irreducible lattice in an adjoint semi-simple semi-simple Lie group not isometric to PSL2R, then every eigenvalue of every element in gamma is algebraic. In fact, more than that, there is some number field and an element in G such that you can conjugate gamma with this element into the group. The adjoint group is a matrix group, the group such that all the you can conjugate like here into the group of rational point, and eigenvalue are preserved by conjugation. So, but it's nice to say it about eigenvalue. And if you know all eigenvalue, actually you can deduce the stronger version from that version. So you can deduce also that from that. That's because if all eigenvalue are algebraic, then you can define the trace field, which is a number field, and you can show that you can conjugate the group into that field. But so this corollary is quite strong, and I think so. Selberg realized that for uniform lattices in SL NR, where n is at least 3, and he proved local rigidity and did this as a corollary. And I think that was his motivation to formulate the arithmeticity conjecture, that every lattice in higher rank is arithmetic. His first formulation was not precise and was later corrected. But so let me explain how it goes, how do you prove it. So here is a very useful lemma. Which I will not prove, but I recommend you to prove it. Okay.
Tsachik?
Yes.
The eigenvalues of an element in the semi-simple group is always the same as the eigenvalues of its adjoint as methods on the Lie algebra.
Okay. So if you take the SL2R and then you suppose, for instance, for this example, SL2R is a SL2C is a three-dimensional complex group, six-dimensional real group. And if you look at the adjoint, for instance, as a complex group, then you see that there will be some other eigenvalue, right? Because if you take the adjoint of that group, then of that element, also pi square will be an eigenvalue. And there will be more eigenvalue, but they are related to the eigenvalue here. So I think if the original group is a matrix group, then if alpha and beta are eigenvalue of an element, then alpha over beta is an eigenvalue of the adjoint. So for any alpha and beta. So yeah, so they're related in this way, but they're not precisely the same. Here is a very useful lemma that I like, and it can be used for various applications. So let X be the real point, the variety, the set of real point of a affine algebraic variety of an affine defined over Q, over the rational. So X is, if you want, X of R, where this is a Q algebraic variety. So X has also it has a Rigidity topology, but it also has a Hausdorff topology. And then so let Q tilde be the algebraic closure of Q in R. So it's the field of all real number which are algebraic, or which are the field of algebraic real number. I don't allow complex number. Then this set is dense in X in the Hausdorff topology. That's the lemma. And so that's the lemma. It's follow, you can prove it from using the implicit function theorem. So X is defined by some polynomial with rational coefficient, and you have a point in X, a real point in X. And I want to show that I can deform it a bit and make its entries. Okay, you can think of all this inside some affine algebraic variety. So it's sub variety of Rn defined over Q, and you have a point there, and you want to say that you can slightly deform it to make all the entries algebraic. So you use the implicit function theorem, and then you have like the free coordinates and the non-free coordinates. And the free coordinates you can just move to rational points. The rational are dense in R, and then use the implicit function theorem to find a solution with such that the free entries are what you want, the rational points, and then the solution will be the other entries will be algebraic. So let me give you, so the exercise is prove the lemma. Using the implicit function theorem. But if you, in fact, the only reference I'm aware of this, so this was, of course, well known to many people, in particular to Selberg. He mentioned this lemma in his paper, but he doesn't bother to prove it. I wrote a proof for it in one of my papers, because I needed the version of this lemma for other local field, not for R, but for also positive characteristic where the proof becomes a bit tricky. So if you can look up so I think this would be, you may look a paper by me and Emmanuel Broya called Uniform Independence of Linear Groups, and there is a lemma there, lemma 3.2 in I think my dentist want to, okay, I will. So okay, so you can look at in lemma on lemma 3.2 in that paper where we do it for general over general local field, which is more complicated, but over R it's a few lines. So it's a nice exercise, and this is very useful lemma, so you should be aware of it. So here is how we use it here. So now so now consider, so let now X be home gamma G. So if G is let's say a matrix group, it's a fine algebraic group defined over Q, and if you want, home gamma G is also okay, it's a real algebraic variety, a fine algebraic variety defined over Q. Why it is defined over Q? It's exactly how I described before. You can think of this as a subvariety of G to the sigma, where sigma is a generating set, and it's defined by the relations that define gamma. So I don't even need the fact that, I need the fact that gamma is finitely generated. I don't need that it is finitely presented. But you see, the affine variety is always defined by finitely many polynomial. This is a Hilbert basis theorem. So even if gamma is not assumed to be finitely presented, you get some variety which is defined over with finitely many rational functions. Okay, but actually I'm not even using it. So so I'm looking at this. So if, okay, we can find a point, let's say Q tilde point, arbitrarily close to the inclusion, to gamma. What does it mean? So we find, so in particular, we find that is a map from gamma to G of Q tilde close to the identity, to the inclusion. Okay. If gamma is locally rigid, it means there is G in G such that G gamma G inverse equals f of gamma. So in particular, it belongs to G of Q tilde. Now, gamma is finitely generated. So there is K inside, so a number field, there is a number field. So a number field is a finite extension of Q. So it's any finitely generated subfield of Q tilde is the number field. Since gamma is finitely generated, so going over all the generators, so there is a number field K such that f of sigma belongs to G of this K for every sigma in sigma, which implies, since this is a group, that for every gamma in gamma, f of gamma belongs to G of this number field. And this is the result. So this implies that G gamma G inverse belongs to G of this number field. So this is how you prove this nice corollary that that elements in lattices must be algebraic or must have algebraic eigenvalues. Okay, so this is one of my favorite applications for local rigidity. The other application is Wang's finiteness theorem. So it's also an application of the other application. I want to mention is Wang finiteness theorem. So it's a beautiful theorem of Wang. I think Wang's paper it's very short. It's only a couple of pages, and it proves a wonderful result. Let me state the result, and then we have a break. So it's only a couple of pages, but it relies on local rigidity and other heavy or at least non-trivial results about lattices. And I'll describe the proof of it after the break. So let G be a semi-simple Lie group actually, also in the previous of all the statements I formulated in the first hour, I should always assume that without compact factor. I sometimes forget to write it. And suppose that it's not locally isomorphic.
What do you mean by without compact factors?
just a minute, not locally isomorphic to SL2R and SL2C. So I want to consider, if you consider just simple group, I just mean that it's non-compact. But for instance, I don't want to consider SL, let's say SL3R cross SO3. This is a compact factor. So every semi-simple Lie group, if it's adjoint, then it's a product, a direct product of simple factor. And I want all of them to be non-compact. So there is this distinction, this one important parameter in the theory of semi-simple Lie group is called the rank, the real rank. And compact means real rank 0. Non-compact means positive real rank. And sometimes we require higher rank. But here I only assume without compact factor, and I don't want it to be like 3-dimensional over R or over C. Because I'm going to use local rigidity, and for this application, the relative local rigidity which we have in SL2C is not sufficient. So for the previous application, relative local rigidity was sufficient. For this application, it's not sufficient. So I need to assume that it's not locally rigid. Then for every V, for every real number, positive real number, there are only finitely many lattices in G of covolume at most V up to conjugation. Of course, if I take a lattice, I can conjugate it. I have plenty of other lattices which are isomorphic, which are, yeah. But if I count them only up to conjugation, there are only finitely many. That's one finiteness theorem. It's a beautiful theorem, which is not true, of course, in SL2R because of Teichmüller theory. You have even one lattice. It has continuously many deformation. Each of them gives me another lattice, which is usually not conjugate to the original one. They're always isomorphic, but as groups, but they're not conjugated.
So is it true that you have only finitely many lattices up to isomorphism, abstract isomorphism?
In SL2R, yes.
But not in SL2C?
In SL2R, it's true, because, for instance, you can deduce it from some version of Gauss-Bonnet theorem. In SL2R, yes, it's true in SL2R. It's not true in SL2C. Even
if you, I mean, up to covolume V.
Yeah, in SL2C, it's not true. In SL2C, if you remember, we had this, we have this picture, which it's a very simple picture, but you draw it and try to explain many phenomena. So one of the phenomena that if you have a hyperbolic tree manifold with a cusp, you can cut it in infinitely many places and obtain a sequence of infinitely many lattices. Each of them has volume which is smaller than the original one. So the volume converges to the volume of the manifold with the cusp, but it's always smaller. Each of them is compact. Each of them is, and they're all non-isomorphic. So that's so in SL2C, it's very interesting. You can construct. Yeah, it's not true. The variant of Wang's theorem, but in SL2R it's true. In SL2C, okay, some variant of it may be true. For instance, okay, we can discuss it, but it's not true in that generality. So that's a theorem. So that's a finiteness theorem. So you know, in mathematics, somehow usually okay, there are some finiteness theorem which with proof are like abstract. You prove finiteness without giving any quantitative version. The proof doesn't give any quantitative version. One example of this is Margulis normal subgroup theorem. Margulis tells you, I mentioned probably this theorem, that if you have a lattice in a higher rank simple Lie group, then every non-central, suppose the group is center free, like SL3R, if you have a lattice in SL3R, every normal subgroup is a finite index. And so it's a finiteness theorem. And the way he proves it, okay, it's a complicated proof, but eventually shows that any quotient, any proper quotient of a lattice is at the same time amenable and has Kashdan property T. And these two properties can live together only for finite groups. So this is a finiteness statement that is proved, by forcing it to be true. But a more common way to show that something is finite without getting a quantitative an effective version is by considering some topology and showing that with respect to some topology, what you're looking at is at the same time discrete and compact. And this is basically what Wang did without actually saying what is the topology, but we will see it. So he showed that with respect to a certain topology, the set of conjugacy classes of lattices in G of volume at most V is at the same time discrete and compact. So compact we will show that it's compact using some compactness criterion, the Mahler-Chabuti compactness criterion, which I'll formulate and prove after the break. And also we apply Kashdan-Margulis theorem, which in this course I still haven't proved, but it's one of the plans for later, but I will state it. So that will imply compactness, and discreteness will be a consequence of local rigidity. And if you combine, so if you want the proof relies, so I said it's a very short and elegant paper. Actually, the original paper had some mistake, but the mistake was because it didn't quote veil properly for the local rigidity, but there was no mistake in the arguments in the paper. But okay, in the original paper, if you look at it, it doesn't assume that the group is not SL2C. It just assumes that it's not SL2R. But okay, the proof relies on four things: on finite generation, which is it's a non-trivial theorem, but okay, in previous courses I proved it, I think. In that course I didn't, but I mentioned it. So every lattice is finitely generated. Two, Chabuti-Mahler compactness criterion, three, Kashdan-Margulis theorem, and four, local rigidity. So all this four ingredient together, if you combine them nicely, then these three together, these two give you the compactness of something, of the set of, conjugacy classes of lattices of volume up to V, and these two give you the discreteness. So, I will, this, if you combine them together, this implies compactness plus discreteness of something, which implies finiteness. And let's have a break, and then I will explain this and move on to the other rigidity theorems. So maybe we do 10 minutes break, and then we'll try to finish.
Let's do 15 minutes break.
15 minutes?
Yes.
Okay, I want to finish at 12:30 anyhow, because I
don't
want
mind
to.
finishing at 12:30.
Okay, so let's do 15 minutes. So we meet again in 10 to 12, and yeah. Okay, so
Great.
see you.
See you.
Okay, and by the way, I'm coming today to Rehovot, so if tomorrow I might be in the department, if someone is coming. Stop. אז טוב, אני נתראה עוד כמה דקות. רגע. so should I start? Yeah, either turn on the camera or say something so I know that you are here, and then I can start. Okay. Okay, I see some of you. Enough. So okay, let's start. Recording. Oh.
Yeah, now it's on.
Now it's on. And what happened in the first hour?
It was
recording.
It was recording?
Yes.
Yeah.
Okay, I just didn't stop it in the break.
Yeah.
Okay. So let's see. Okay, so let's go over this 4 ingredients. All of them are important theorems by themselves. So the first is that lattices are finitely generated. Lattices in actually Lie groups are always finitely generated. For semi-simple Lie groups, actually this was well known, but I think the only place it's written in that generality is in my note with Raz, but it was well known long ago, but it was an open problem for a while, which was actually the motivation for Kashdan one of the main motivation to prove to define property T. He showed that lattices in higher rank group admit property T, and property T implies finite generation. And again, in rank 1, it was proved by Garland Raghunathan. And Garland Raghunathan in the paper about lattices in rank 1 that I mentioned earlier. And so this is now the modern, the original proof. I wrote a geometric proof of that based on Gromov's idea, but it is well known, and we will use it. Yes. The other theorem is the compactness criterion. So Chabuti Mahler, maybe I should, how do you spell Chabuti Mahler? Maybe you can help me here. I would never know to spell Chabuti, so let me just call it Mahler. Maybe is that okay? Mahler compactness criterion. And Mahler stated it for lattices in Rn, and Chabuti stated it for more general lattices. So the theorem is the following. So first, I need to recall the Chabuti topology. So did I discuss in this course the Chabuti topology or not? No. So I need to say something about the Chabuti topology. Okay. So I need to know how to spell Chabuti anyhow.
No, it's Chabauty.
Chabuti Mahler compactness. Okay. So the Chabuti. So let's start by
the Chabuti topology, and then you won't know how to say it, but you will know how to spell it.
Okay, the Chabuti topology So it's the topology of closed subgroup. That's how I prefer to call it, and you understand why. So sub G is the set of all closed subgroup and there is a topology. The topology is defined by the generators of the topology are of two kinds. A subbase for the topology is given by the topology is generated by sets of the following form. One is O1 of U, which is a set of all H in G closed such that H intersection with U is not empty and U is open. And two, you have sets of the form of 2K is sets of all H in G closed such that H intersection with K is empty. And now K is compact inside. So that's the generators of the topology, and that's a topology of closed subgroup. Exercise Hn converge to a limit if and only if the following holds. Hold. One, for any H in H, there are Hn in Hn such that Hn converge to H in the usual topology of G. Two, for any Hnk in Hnk, a subsequence such that Hnk converge to a limit, admit a limit, the limit is in H. So that's a sequential formulation of this topology. This topology, actually another exercise, this topology is metrizable. Okay, I will not go into that at this moment, but another exercise, which again, all these exercises can be found in the literature, like propositions with proof, but I think it's nice to think about them. Then the space of closed subgroup with the Chabuti topology is compact. And this is for any, in our case, G is a Lie group, but in general, it's true when G is, I think, sigma compact or locally compact second countable group.
Tsachik?
Yes.
So in the first exercise, just one of the following has to be old?
If the following, no, both of them, following
Both of them?
conditions.
Okay, thanks.
By the way, the content of my lecture today is included in the fourth lecture of my PCMI lecture series, which is on archive. These 4 lectures. What I'm doing today is part of the 4th lecture. Okay, and then the Chabuti-Mahler criterion is the following. So, the compactness criterion. Okay, maybe I'll give you another exercise. Let G be a Lie group. And gamma is discrete subgroup. Then there is a neighborhood of gamma in sub G consisting of discrete subgroup. So if you are close to be discrete in the Chabuti topology, you must be discrete. And the hint, use NSS, which no small subgroups. So you remember what distinguishes a Lie group from other groups is that there is an identity neighborhood such that the only subgroup of this neighborhood is the trivial group. So one side is not so hard, that if you are a Lie group, then you have this neighborhood. The other side is the Hilbert fifth problem, that a group with no small subgroup is a Lie group. That's a classical theorem, but I wanted to use the more standard side, that if you're a Lie group, then you have no small subgroup, and you use that to prove the exercise. Okay, that's independent for the compactness criterion. Oh, again, another exercise. Okay, the compactness criterion. So, okay, actually I can formulate it in three conditions. So, given identity neighborhood U in G, the set for gamma in sub G, all discrete subgroups, such that gamma intersection U is the trivial element, is closed. Is that true? So yes, it's closed. Two, given V positive, the set of all, let's, given V positive, let's do it this way. If gamma n inside G are lattices and gamma n converge to a limit, in the Chabuti topology. Then the core volume of gamma can, so there is less semi-continuity. The core volume of gamma is smaller or equal than the lim inf of gamma n. And the corollary, hence, given U open and V, the set of all gamma in G such that gamma intersection U is trivial and the core volume of gamma is at most V is compact. So let's call this 1 and 2. And yes.
So
And one is
why is the limit a discrete subgroup as well?
because of 1.
But you don't know you have a single identity neighborhood for all of them.
No, no. What do you mean?
Why is the limit of discrete groups discrete?
I mean, you don't want them just to be lattices, but you want them to be uniformly discrete, having a to admit one U.
Okay, that's the criterion. Let me call it this is the theorem. Given an open set, given U and V, the set of all discrete group for lattices that intersect U trivially and of core volume at most V is compact.
Okay, but for what you're outing to, it's always true if it's true if there is one U.
Here I want to assume you're right. Here, if gamma n are lattices, gamma n and gamma, yes. Or if gamma n are lattices, and let's say and gamma is discrete.
Okay.
Yeah, you're right. Thank you. It's true that it could be that discrete group converge to a non-discrete group, like think of Z inside R and then multiply Z by some numbers which converge to 0, then you get denser and denser discrete group. The limit is R itself, which is not discrete.
So
yes,
this
so
is true for every locally compact group?
yes, this compactness criterion is true in every locally compact group. So this let G be a locally compact group, and then the following is true. Yes. And okay, to prove the compactness criterion, you need to prove 1 and 2. 1 is obvious, right? One. I mean, if you have a sequence of groups that intersect U trivially, and they have a limit, then the limit also intersects U trivially, because if the limit intersects U, then there is some open neighborhood of it that everything there intersects U by the generator of the Chabuti topology. Remember this first type of open set is exactly that. So 1 is obvious. So how to prove 2? So it's enough to prove 2. To prove 2, observe the following. that observe the following fact. Fact 1, if omega, or let omega be a fundamental domain, or let's say a subset K in G injects into G mod gamma. So in particular, so it's the same as saying that it's contained in some fundamental domain. You can extend it to a fundamental domain if and only if K inverse K intersect gamma trivially. Right? You see that? Because what does it mean not to inject? You don't inject, K does not inject if there is K1, K2 in K, and gamma in gamma. K1 is not K2 and gamma is not the trivial element, such that K1 equals K2 times gamma. So it means that K2 inverse K1 equals gamma. Okay, so fact 1 implies fact 2 that the co-volume of gamma is the supermum of the Haar measure of K such that K inside G is compact and K inverse K intersect gamma trivially. You see that, right? Because the co-volume of gamma is the volume of the fundamental domain, the Haar measure. This is how. The co-volume of gamma is the Haar measure of the fundamental domain, which is the supermum of the Haar measure of compact subset of the fundamental domain. And K is inside the fundamental domain if and only if it satisfies this condition. This is by fact 1. So together with these two facts, you see that this implies a compactness criterion because, okay, proof of the compactness criterion of star. So let gamma n be lattices such that gamma n intersect U trivially and co-volume of gamma n is at most V. Then gamma n converge to a limit. There is a subsequence, of course. The Chabuti space. Okay. Let.
Tsachik, what about proving number 2?
Number 2. What do you mean number 2?
In order to prove 2, we had 2 facts, and now we're proving the corollary.
Ah, okay. So it's enough to prove number 2, right?
Yeah.
No.
It's the same proof. To prove the theorem and to prove number 2 is the same proof.
Okay.
Right. So I want to show. Okay, proving the theorem. Let's say is the same as proving number 2. above. So okay, let's call this A and B. So I'm proving number 2. So gamma n converge to gamma. We need to show that the core volume of gamma is at most the core volume of gamma n. So let K be a compact subset. Let K and G be compact such that K inverse K intersect gamma trivially. Since gamma n converge to gamma, K inverse K intersect gamma n trivially for large n. So this is the second condition, the second type of generators of the Chabuti topology. If this intersection was not trivial, then it was not trivial in the limit as well, because K is compact. So K inverse K is also compact. And therefore you have that. So this implies that the core volume, this implies that K inject into G mod gamma n, which implies that the core volume of gamma n is at least the measure of K. Now K was arbitrary, so by fact 2, we get that the volume that okay, we get a theorem. We get that core volume of gamma is smaller than the lim inf. Okay, that's the Chabuti-Mahler criterion. Now, the last ingredient, which is something that we discussed a lot in previous courses. Okay, we discussed today local rigidity, but so the last ingredient, I mean, Kashdan Margulis, let me just state this theorem. So this is a beautiful theorem that by today there are several proofs.
Sorry, we didn't show that it equals the limit by regularity of the measure or something.
No, but
Okay, is it equal? I think that's I think it's equal, but there is something to prove it. So that's actually a wonderful exercise. Let gamma n converge to gamma lattices, B lattices. Is it always true? B lattices under what condition? On G, I don't remember the answer. That's why I ask it so vaguely. Maybe it's always true, but maybe I need to assume a Lie group or something. But maybe it's always true. I need to think about it a moment. We can say that that the volume of G mod gamma n converge to the volume of G mod gamma. So we just proved that the volume of G mod gamma n, the lim inf is bigger. Yeah, maybe it's always true. Somehow, actually, okay, maybe we will, okay. So for the moment, it's an exercise. Maybe we will need to prove something like that for the application. So I will not have time. Okay, I see that it's always like that when lectures on Zoom, you talk even much slower than frontalic lectures, but at least let me formulate the Margulis Theorem. This is another wonderful theorem, which is the last ingredient that we need in order to prove the Wang finiteness theorem. So and this is true in general. Now, for any semi-simple group, also SL2R, let G be a connected semi-simple group. Then there is an identity omega in G such that for any, now you don't need even to be discrete, for any, you don't even need to be a lattice, for any discrete group, let's say lambda inside G, there is G in G such that G lambda G inverse intersect omega trivially. That's Margulis theorem. This is this theorem has very nice application. For instance, it implies that there is a lower bound on the co-volume of lattices, and this is true in general. So here we prove some finiteness theorem. We prove that for every V, there are only finitely many lattices of volume at most V. Before that, Margulis proved the following. So here is one corollary. For G as above, there is V such that for every lattice gamma in G, the co-volume of gamma is at least V naught. So this was not known. So you know, for in particular, it implies that there is a lower bound on the hyperbolic tree manifolds. And then some people dedicated many years and very serious and hard mathematics to calculate and to find the lowest volume manifold. So it's not trivial at all. But the fact that there is lower bound is due to this elegant theorem by Kashdan and Margulis. And okay, I want to finish soon because I want to go to the dining room in the kibbutz and it's closed soon. But at least you see, I will explain it in the beginning of next time. But you see the idea. So now you have a lattice. You can always conjugate it to intersect trivially some identity neighborhood, which is the Kashdan-Margulis neighborhood. So if you want to prove finiteness theorem, like Wang's finiteness, that there are only finitely many conjugacy class of lattices of volume bounded by V, then from any conjugacy class, you can pick a representative which intersect this special open set trivially. So you just need to consider lattices that intersect omega trivially. Now you have this upper bound on the volume by the assumption, because you fix V and you only consider lattices of volume up to V. So you can apply the Chabuti compactness criterion and say the lattices which have volume at most V and intersect omega trivially is a compact set. And now, finally, you want to say that this compact set can be covered. So every conjugacy class intersect this compact set in an open set. And this is basically local rigidity. Say that if two lattices are closed, then they're conjugate, which in other words, every conjugacy class is open. But there is some trick here. The game is not over because there are two different topologies. So local rigidity is formulated with respect to the topology of representation variety, the space home gamma G. While now we discuss this compactness with respect to the Chabuti topology. So you need to pass from one topology to another, and for this you also use this finite generation of lattices. So we will do it. It's like it will take 5 minutes, but now I have only 3. So so we'll do it in the beginning of next lecture, and I will continue next lecture to discuss this other rigidity theorem. So any question? Okay, so thank you. Stay safe. So you're in Tel Aviv, most of you? Itamar, Paul.
Yeah, I am.
I'm in